Hello students, I hope you're having a wonderful day. Today I would like to complete a practice problem from chapter 8. So we are going to solve for two support forces. So students are holding up a board and there's two boxes on the board. So let's go ahead and get started. I'm going to read the problem and we're going to write down some knowns and we're going to draw a picture before we answer the three parts of the problem. So two students are holding up the ends of a 5.7 kilogram board that is 2 meters long. An 8.5 kilogram box of car parts rests 0.75 meters from the left side of the board, and a box of tools with a mass of 14.2 kilograms rests 0.75 meters from the right side of the board. So before we get into part A, B, and C, let's just draw a simple picture to represent what's going on. So here we've got a student on the left side, and we have a student on the right side here. We have happy students, and we have two boxes that are resting on the board, okay? So if we're going to draw some dimensions here, I'm going to call this student A, and on the right side here we have student B. And so we know that the left box, the center of this box, rests 0.75 meters from the left side of the board. Okay, and then this guy, this dimension here, if the board is 2 meters in length and this box is resting 0.75 meters with respect to the right side, that means our dimension here is 1.25 meters. And I will go ahead and draw an overall dimension. This will be 2.0 meters, okay? Now, what we need to do is go ahead and draw a free body diagram. As you can see, part A says draw a free body diagram. So we're going to draw the board. We are going to have the weight force of the board acting in the very center of the object. So we're going to represent this F sub G, the weight force of the board. We're going to calculate that. So we have F sub G sub board. This is going to be the product of the mass of the board times the acceleration due to gravity. And it says the mass of the board is 5.7 kilograms, so 5.7 kg, times the acceleration due to gravity, negative 9.8 meters per second squared. So let's go ahead and grab our calculator. I've got 5.7 times a negative 9.8. So the weight force of the board is a negative 55.86, and we're going to have units of newtons. We know a kilogram meter per second squared is equal to a newton. Now, we have a negative value because force, weight force, is a vector and it's pointing in a negative y direction. We are going to give it a value of 55.86 newtons here because we have a vector arrow that's pointing in the negative y direction. Okay, moving on. So we have an 8.5 kilogram box of car parts resting 0.75 meters from the left side. So we're going to have an applied force. I'm going to label this F sub G. So we have car parts, and it is 8.5 kilograms. So to calculate the weight force of the car parts, I have 8.5 kilograms times a negative 9.8 meters per second squared. So on our calculator, I've got a negative 83.3 newtons. Let's go ahead and label our free body diagram. Okay, 83.3 newtons, and our vector arrow is pointing in a negative y direction. Next, we have some tools, and we need to calculate the weight force of the tools. So F sub G sub tools, we have 14.2 kilograms times a negative 9.8 meters per second squared. So 14.2 times negative 9.8 will give us negative 139.16 newtons. So we're going to go ahead and identify this on our free body diagram. So, weight force of the tools, once again, numerically I'm going to have a positive value here because our vector arrow is pointing in a negative y direction, so 139.16 newtons, okay? I'm going to need some room here, so I'm going to erase all of my calculations for our weight force. So remember that on the left side of the beam, I describe this is student A, so I'm just going to put an A here. We are going to have a support force at A, so we have a student A holding up. I'm going to call this F sub A sub Y. The reason I'm using the subscript of Y here is because our student is applying a force in the positive Y direction. Next, we have student B on the right side here. So we're going to have a support force, F sub B sub Y. Okay, now the only thing left that we have to do is show some dimensions here. So right here, where the weight force of the car parts is acting, this is 0.75 meters, and this is with respect to point A. Then we have the weight force of the board acting at the beam's central location, so we know that the beam has a span of 2 meters, so this is going to be 1 meter. Then, where the weight force of the tools is acting, this is 1.25 meters. And then, as I mentioned earlier, the span of the beam is 2.0 meters. Okay? So, we've got something that looks like that. So, we fulfilled part A. We've drawn a free body diagram. We have identified the 5 forces that are applied to the beam. We have 3 weight forces, and we have 2 support forces. So we have 5 forces in total on the free body diagram. Moving on, part B, calculate the forces the students will apply to each side of the board, and these are known as support forces, okay? So we're going to start at point A. Now, we're going to sum the torques about point A. So I'm going to use the capital Greek letter, sigma, sum of the torques about point A. So sigma T sub A. And now, we're going to have an axis of rotation at part A. So if you can imagine this in 3 dimensions, this point that I've drawn on the board is an axis of rotation. Remember that torque, whenever we're talking about torque, what we're doing is describing the tendency of a force to cause a rotation. So torque is equal to your applied force times your lever arm, okay? And we know that a counterclockwise rotation represents a positive direction for rotation, okay? So we're going to start right here at point A. Now at point A, we do not have any torque, okay? Because torque is our applied force times our lever arm. We're at a position of 0 meters on our beam here, or our board, okay? Now, if our position is 0, if our lever arm is 0 meters, and you plug that in here, 0 times any force applied, well, our torque is going to equal 0. And just visually, you can see that there is a support force applied at a position of 0 meters, but we're not going to have a torque at 0 meters since our lever arm is 0, okay? So we're going to start at this position, 0 meters. We're going to move in a positive x direction. So we're going to take into account where we encounter our first force. So moving in a positive x direction, nothing's going on, nothing's going on. Oh, until we get to a position of 0.75 meters. We have an applied force, so we have a weight force of the car parts. So what we have is 83.3 newtons. Remember, A is an axis of rotation. So this applied force will cause a clockwise rotation, and that's negative. So I have negative 83.3 newtons times the lever arm, 0.75 meters, plus, okay, we're at 0.75 meters. Now we're going to move in a positive x direction and until we get to our next force. That's going to be the weight force of the board, and we're at a position of 1 meter. So I've got a negative 55.86 newtons multiplied by the lever arm of 1 meter. Bear with me here, I'm running out of room. Okay? All right, so we're at a position of 1 meter on our board. We're going to move in a positive x direction until we encounter another force. So moving on, here we have another force. We have the weight force of the tools. Okay, so here we have the tools in our box. Okay, so plus, now we're going to have another force that's causing a clockwise rotation. So I have a negative 139.16 newtons, and we're at a position on the beam, on the board, with respect to point A of 1.25 meters, plus, so moving on, we're moving in the positive x direction, nothing's going on, until we get to a position of 2 meters and we have a support force or reaction force. And look at the vector arrow, and remember, this is our axis of rotation, point A. This is going to cause a counterclockwise rotation. And hey, look here, we've identified that a counterclockwise rotation is positive. So we're going to have a positive value for F sub B sub Y times 2 meters. And we're going to set all of this equal to 0. So the torques, the sum of the torques will equal 0. And the reason it's 0 is because our board should be in a state of equilibrium. Okay? So let's take out our calculator, and then we're going to take the product of these two values here. I've got a negative 83.3 newtons times 0.75 meters. That will give us negative 62.475. We have units of Newton meters, plus I've got a negative 55.86 Newton meters, plus, okay, now we're here, we're going to take the product of these two values. I've got negative 139.16 times 1.25 meters. That is a negative 173.95 Newton meters, plus support force B times 2 meters is equal to 0. So what we want to do is add these three values. They have like units, okay? So here we go. I've got a negative 292.285 Newton meters plus support force B times 2 meters is equal to 0. So what we're going to do is isolate support force B, okay? How we're going to do that is we're going to add 292.285 Newton meters to both sides of the equal sign. Then we're going to divide by 2 meters on both sides. So this is going to look like this. Support force B, F sub B sub Y, is equal to a positive 292.285 Newton meters. We're dividing this by 2 meters. As you can see, our units of meters are going to cancel. Boom. Leaving us with units of newtons, and that's great because you know in the metric system, force is in units of newton. So we're looking good there. So I've got 292.285 divided by 2. This is going to give me a positive 146.1425 newtons. Okay? And so on my diagram, what let's do on the free body diagram is go ahead and label support force B. Okay? 146.1425 newtons. Okay? All right, so next what we need to do is calculate support force A. So the force that student A is applying in a positive y direction to hold up his end of the board. Okay? So I'm running out of room here. I'm going to erase all of this business. All right, so now since our board is in a state of equilibrium, that means that our forces in the negative y direction and our forces in the positive y direction will be equal in magnitude, but the vectors are pointing in opposite directions. So we can write an equation there. We can say the sum of our applied forces, let's just plus the sum of our support forces are equal to 0. And once again, we're setting this equal to 0 because our beam is in a state of equilibrium. So our applied forces, this is going to be the weight force of our car parts plus the weight force of the beam plus the weight force of our tools. Okay, so those are our 3 applied forces. Now, the sum of the support forces. We have support force A, F sub A sub Y, plus support force B, F sub B sub Y is equal to 0. Now we need to fill in some values here. So just starting left to right here, let's do a negative 83.3 newtons. Remember, it's negative because this weight force vector is pointing in a negative y direction, plus the weight force of the beam, I've got negative 55.86 newtons, plus weight force of the tools, a negative 139.16 newtons, plus support force A, plus support force B. We're going to use our calculated value that we just received, 146.1425 newtons is equal to 0. Okay? So we need to add the values here. So we can do that because they have the same units. They're all force values. So I get negative 132.1775 newtons plus support force A is equal to 0. So to isolate our support force A, we're going to add 132.1775 newtons to both sides of the equal sign. I'm going to go ahead and label our diagram here. So student A is applying a force of 132.1775 newtons in a positive y direction. So we're adding this to both sides of the equal sign. I've got 132.1775, and I'll just put my unit of newtons right there. So we've taken care of part B. On part C, it says create a graph showing both support forces. So this is going to be a bar graph. So on the x-axis, I'm going to have support forces. There we go. Let's do that a little bit neater there. Okay. So I've got A and B. On the y-axis, I have force with units of newtons. Okay. And Let's just go, I don't know, let's create a scale maybe going up by 25s, okay? Okay. All right, so support force A, we calculated that to be 132.1775. Okay, there we have support force A, and then support force B, we calculated at 146.1425 newtons. Okay, there we go. There we have it right there. So, I hope me solving this problem for you and working it with you today has helped answer some questions for Chapter 8, Calculating Support Forces. As always, if you need any help or have any questions, you can send me an email, you can give me a call on my office phone, or you can contact me over Canvas. So, thank you, and I hope you have a wonderful day.